Well, welcome to the G2M Research Multi-Vendor Webinar on Scale-Out Flash Storage Solutions. Our sponsors for this webinar are Toshiba, Accelero, and Lightbits. Just a quick kind of look at the agenda here. So I'll spend the first few minutes going through the ground rules and introducing the topics. Then each of the three vendors will give a presentation that will take about 8 minutes apiece. After that, we'll go into the key questions that we'll ask the panel. Each panelist will get 2 minutes to answer that question, and we'll have 4 questions altogether. And in between these, we'll have audience survey questions. The audience survey questions tend to be they're all single choice, but on the second question, there's multiple questions as part of that, so please hit each one. After that, we will go into the audience Q&A and wrap up about 10:20. Couple reminders for the audience Q&A, please put your questions into the Q&A window on Zoom. If you haven't used it before, just go ahead and click on the top banner and click Q&A, and you can do the questions there, and then just put them in as you think of them, and once we hit the Q&A section, we'll go through them. And with that, let's go ahead and get started. So my name is Mike Human. I'm the managing partner of G2M Research. With us is Joel Detrick. Joel is the VP and GM of Network Storage Software at Toshiba. We also have Josh Goldenhar, VP of Products at Accelero, and Cam, who is the VP of Strategy and Business Development at Lightbits. So what is a scale-out flash storage solution? It's a good question. For all those who have known about software-defined storage, scale-out flash storage is kind of an outgrowth of that, but it differs in some fairly fundamental capabilities. What it really is a combination of a software package and a multiple number of servers. These could be storage servers, these could be standard servers that contain NVMe storage devices. As we said, it kind of evolved from software-defined storage. One of the big differences, though, is SOFS can scale out to hundreds or even thousands of nodes. If you think of the typical software-defined storage of the previous generation, Exentis, things like that, usually you had a couple nodes, maybe 3 or 4, but that was typically it. So this is something that can scale out significantly higher than that. It kind of borrowed on the whole concept or storage architecture that the hyperscalers were using in their DAS environments, where they first started standing up lots of DAS storage to save money, and then started figuring out how to network those together. So that's one of the ways they built on it. One of the big things that has enabled it, though, is using NVMe over fabrics as the way to communicate between those nodes. The big difference that provides is it allows incredibly fast storage with very low latency, near local file system performance. So that's kind of one of the big differences with SOFS and the old software-defined storage packages. One of the questions I always get asked is, what's the difference between an SOFS solution and all-flash RAID? To me, there's about 4 really important ones. One of them, it's definitely a strength for SOFS, is you can combine different heterogeneous servers and SSDs into a single uniform storage pool. It doesn't matter if I'm using HP servers or Dell servers or Supermicro or Lenovo or a combination of all those. I can put them all together and have it look like one namespace. Same with the storage devices. These could be anything from Optane storage devices to standard NVMe SSDs of varying speeds, and I can make it all look more or less the same. Scale of deployment, obviously we talked a little bit about that, but the ability to scale into hundreds or thousands of nodes across a data center means that you can put storage really where it's needed, but yet make it accessible to everything. And I'm sure our panelists will talk more about that as we get into the discussion. One of the third ones is the ability to have, the 2 of the negatives, I guess, or 2 of the negatives that Ray got, and we'll have our panelists talk a little bit about this, is that in an SOFS solution, you have to combine the software with hardware from a different company. The Ray guys would say it's one throat choke. I think what we've seen over software-defined storage and FOFS evolution is that SOFS companies have gotten pretty good supporting this. So I also want to talk about that later. We'll let them do that. And then that kind of fits in the complexity of support model as well. Again, These are things that I think the array guys would throw out. I don't think that it's much of an issue. So really, from a user perspective, if you start thinking about, do I want to do this, there's probably 3 questions you need to ask yourself. Number one is, what are your use cases for your storage systems? Are they ones that can really take advantage of SOFS? I think there's a lot more opportunities now that can really take advantage of it, and I know that our panelists will talk about some use cases that they've seen in their practice of doing that. The second one is maybe thousands of servers or storage appliances plus software the right choice for you? Certainly for a lot of environments, it makes a lot of sense. Certainly from a standpoint of uniformity of performance and ability to grow things where you need it, it has a lot of advantages over centralized or set of centralized arrays. And then third, how do you buy and support it? So we'll talk about all 3 of those things as we jump into each of the users' presentations. And with that, Joel, let me pass over control to you and let you part of the presentation.
Thanks, Mike. I am Joel Diedrich again with Toshiba Memory Corporation. Let's see if I can get this going. So I'm going to talk about scale-out flash storage, trickle-down IT, and the journey to the cloud. As you'll see in a moment, I think that scale-out flash storage is really about the cloud, and so we should define terms there. A cloud to me, you know, everyone has their own definition. A cloud to me is determined by how work is assigned to machines. If you have fluid automated assignment of a workload to machines, that's a cloud. If you have a permanent silo of machines that run single applications, that's not a cloud. And so I will talk about, you know, what problem does scale-out flash storage solve? Who really needs this, and why? And why now? What's wrong with the alphabet soup of network storage transports that have existed for many years? What's different this time? Is this just another entry in the alphabet soup, or is there something really new here? And then why Toshiba? We one of these things is not like the other. We're clearly not a software startup, and we're probably best known for things other than storage software. So I will mention a few words about why we're doing this. So first, why? Cloud infrastructure, as Mike mentioned, in the first kind of generation was very uniform. Everything's a node, nothing is shared. The sort of middleware, the databases and other application underpinnings are offered as a networked service, and those architectures provide infinite scale, but pretty high latency. I mean, that basically the cloud is a deal with the devil. You trade away all of the application richness and semantic richness of SQL databases and all the things we've gotten used to in order to get a situation where the user experience for the billionth user is the same as for the first. The exception is block storage, and by which I mean flash. It's mostly direct attached SSDs, so it's not a network service. Those are fast, but they're ephemeral. Then when the node powers down, the data goes away, and is not really effectively available to share. And that's the way it was done 10 years ago or so. What are the problems with this? Well, one is whatever size SSD you pick will be wrong. The fluid assignment of applications to machines means that the needs of those applications change, and having a fixed amount of storage per machine is pretty non-optimum. Here's another thing, and this slide is really central to our entire thesis and my kind of belief system about how IT works these days. I think important advances in IT technologies now come mostly from Google and Azure, and sort of diffuse downhill from there. They have machines that are growing rapidly, and so they have the economic incentive to invent things that are more efficient. And there's an example of that is the adoption of NVMe SSDs, which was led by the hyperscale guys and is now kind of diffused to the right on this graph from there. The second kind of tier of companies in terms of IT spend are cloud native companies that are not of a scale that allows them to invent all of their infrastructure as the Googles and Azures do, but they do create kind of unique or high leverage pieces and then piece together the rest with help from vendors like us. And enterprises basically can't invent infrastructure, they adopt it when the OEMs can do the engineering for them. So this is a fundamental. If you want to know what enterprises will be doing in 15 years, go read Google research papers and find out what they were doing 5 years ago, and it'll be a very good bellwether. NVMe over Fabrics, I think, has been well adopted in hyperscale already, and will move to the right at the usual rate. And so this is a predictor that we believe strongly in. So what's coming next? The next generation really is to disaggregate and share that storage so that every node can get exactly the needed capacity. You can virtualize and customize the storage for each application, and you can change it rapidly. And the enablers for this include NVMe over Fabrics, Clo networks, which I'll mention a little bit more about, and the advent, the very rapid growth in network cross-sectional bandwidth relative to the growth rate of compute performance and storage capacity, which was also driven by the tier 1 hyperscalers, and luckily for the rest of us is now available to us. So why do this now? What's different now relative to the days of Fiber Channel and iSCSI and all of the other, certainly network storage isn't the new idea. Why will this time be different? I want to, again, say a couple of words about the history of hyperscale and why it's predictive of what we'll see in customers served by the people on this call. One area is the evolution of network architectures. On the left, you see a typical enterprise network architecture. It's highly oversubscribed at every level, and frankly, the reason that Ethernet is cheap has nothing to do with Ethernet. It's more to do with the fact that TCP allows you to oversubscribe a network conveniently, and so it's relatively efficient to build. There's one path from any input to any output, and so locality matters. If you care about latency or bandwidth, you want to put things close together. In the public cloud, that network doesn't exist anymore. Clo or fat tree or flat networks are the norm. There's very little oversubscription. Started off at 4 to 1 and is down to basically 0 now. Many paths from any input to any output. And importantly, locality now doesn't matter. This was enormously expensive. Why in the world did these guys spend the amount of money it took to multiply the number of switches and network ports? Well, this is interesting. When did this happen? In the case of Google, the last oversubscribed kind of conventional network was taken out of service in 2006. Facebook, beat their chest pretty hard in 2015 about their data center fabric and their leaf and spine network. And I think the guys at Google must have just kind of chuckled about that. They were well into their 4th generation by then. But the point is, these guys have driven network bandwidth really hard and driven the cost per bit per second down really hard. And so that gives the rest of us an opportunity to ride on that. Why did they do it? Well, simply because if you can workload blend, you can get the same work done with many fewer machines, 30 to 60% fewer machines, which if you're running Google's cloud is a big number of zeros. And in return, that requires everything being equally network close, and it requires networked flash at the speed of local SSDs. So that return, we're back where we started. This is why Google and others have driven network costs down to the point and driven the networking technologies to the point where we can talk about network flash storage at locally attached speeds. Oops, sorry. The other thing is, this is a special moment in history. I think a lot of people don't realize how profound NVMe is. There are lots and lots of storage transports, but there are really only 2 command languages that matter. SCSI was invented in 1982 when 2 hard drives on your ribbon cable was high performance storage. we went 30 years before we got another command language for storage. It's the only one that makes no pretense of backward compatibility with hard drives. And I fully expect we'll spend another 30 years finding better and better ways to pipe NVMe commands around. This is a once in a career event, and it's going to take over very rapidly, I think. You should not overinterpret this chart. This is Joel Diedrich's personal opinion about what's going to happen and has no Toshiba intelligence applied. But I believe very strongly that if you look at the sort of command sets flowing around data center networks, it's going to flip from SCSI dominated to NVMe dominated very, very rapidly now. And so that tells you that NVMe flash will become the mainstream primary storage for cloud architectures, and scale out flash implemented by NVMe over fabrics will be the way that storage is offered as a service rather than a directly attached inflexible ephemeral device. And we think that's more than just the latest technology. That's a very powerful trend that will have very far-reaching consequences. And then finally, why Toshiba? We're known for a lot of things, but one thing you may not know is that Toshiba memory, which is the flash memory and solid-state disk part of the Toshiba conglomerate, was recently spun out and is now privately held. We hope we'll become a public company again soon. We are the inventor of NAND flash, and our factory in Yokkaichi is responsible for sort of roughly a third of world output, plus or minus. We make flash and SSDs, and now storage software only. And a sort of human interest story here, kind of, people don't realize that flash fabs are enormous by comparison to, for example, microprocessor ASIC fabs. They produce just a river of silicon. The little picture on the right shows the height of a stack of wafers that we would produce at Kaichi every year. So anyway, we are a big manufacturer of flash. We're interested in making the world a better place for NVMe, and my personal crusade is death to rotating rust. So with that, I will turn things back to Mike.
Thank you very much, Joel. That was great. Okay, Cam, let's go ahead and, well, let me see if yours is next or not. Hold on a second. It's Josh. I'm sorry about that. Josh, let me give you remote control. All right, you should have it.
Great, thanks very much, and thanks very much for the opportunity to talk here. Welcome everybody. I'm Josh Goldenhar. Actually only one A in my name there. So I guess today I can be Josh Goldenhar, and VP of Products for Accelero. And with that, we'll go ahead and get started on a slightly different take. So Accelero makes a product called NVMe-oF. It is a play on NVMe, of course. It's a way to take NVMe and mesh it together in your environment. As in per Mike's opening slides, talking about the fact that the goal here, or his definition of SOFS, is to go ahead and have multiple drives across multiple servers all appear as a single storage pool. We are in full agreement with that. That is how we started the company, and hence that kind of term mesh, which is to take multiple servers, allow networking to connect all those drives to all the clients or initiators, and therefore you really truly have one single pool of block storage in a fully distributed block solution. So NVMe-oF is just that. It's a software-defined product. It is software only, no hardware components, no special hardware to buy. You can either have your selection of RDMA NICs if you want the most consistency, lowest latency, highest performance. And if you don't need that, if TCP is good enough for you, I actually fully agree with Joel from Toshiba that TCP was invented and allows for the oversubscription of Ethernet networks. So that means that if you have a whole bunch of TCP hosts competing, TCP will guarantee the delivery of those packets, but you don't know exactly when they're going to get there. So if you want consistency, you'll stick with RDMA, but if you want to go ahead and TCP is good enough for you, we support that as well. So we're all about choice. choose the server of your choice, the drives of your choice, and the networking of your choice. And lastly, that choice extends to, now of course, everyone on this call is block storage. We don't force anyone to choose a particular file system. You use the file system of your choice. So we are the lowest overhead when you want that, TCP when you don't need those levels of performance, 100% software, protocol of your choice, and of course, block storage. And what's more interesting than a deep dive on the product is what are customers actually doing with that. We have many, many customers, many public customers, and actually many more customers that we actually cannot reference. We can only talk about them in those kind of vague terms. But there's a couple interesting things here for folks who are looking at what can you do with shared NVMe? What can you do with NVMe over Fabric? And what folks are doing specifically with Accelero NVMesh is what I'm going to talk about here. So one that we have very recent is a company called InstaDeep. They are offering AI as a service. So AI has a lot of buzz, and this is very true about what was initially talked about. I think Joel mentioned it, that whatever drive you pick is going to be the wrong size. And so we see this as well in these GPU servers, in the NVIDIA DGX line, as well as servers from folks like Lenovo and others. I think Dell just came out with a very nice new GPU server, but they all have a limited number of NVMe you can put inside, and then you're going to have to pick a size. And worse, when you do AI, you're going to go through different phases. You're going through your training phase, which is extremely I/O intensive. You're going to want to use all those drives, but you may also use those same servers for inference. And when you do inference, you don't need a lot of storage. You don't need a very high bandwidth of storage, which means that expensive NVMe you have sitting in your servers, if it's local to one particular server and it's doing inference at that point, it's just not using the storage. So InstaDeep recognized this, that they were not getting the benefit of all their NVMe. And they have DGX systems. So using a partner that we use, Boston Storage, Boston makes an appliance called Talon. It comes in a couple different variants and provides as much as 80 gigabytes per second of bandwidth out of a single 2U chassis. And using that, InstaDeep can go ahead and disaggregate their storage. And not only can they use one of those chassis, if that's not enough capacity or enough performance, they can go ahead and add additional chassis. And NVMesh stripes the volumes across those. And what InstaDeep found is that they could get much higher utilization rates of that NVMe flash across the network. They can go ahead and scale out whenever they need to, and they maintain the latency and consistency of performance. So very, very high bandwidth, especially for the training runs, and very low latency on inference. So that we get the benefits of NVMe, but we don't have the detriment, as Joel was saying, of having local drives only accessible there. We can go ahead and share these amongst many systems and get maximum utilization out of those drives. So next we'll go to a totally different kind of use case, Technicolor. I assume a whole bunch of people out there like movies, and I can't talk about which particular movies, but suffice it to say that NVMesh was used on an award-winning film that was nominated for 6 Academy Awards very early this year. And if you like superhero movies, you've probably watched something on the screen that was post-production color corrected by Technicolor. And what we mean there, for folks not familiar with media and entertainment, is that when a film is done, it has to go to a company like Technicolor for some visual effects processing, for color correcting, that is making the colors appear like the directors and the producers and everybody wants them to look like. And when you're recording something in 4K, which everybody's probably heard about 4K TVs, when you have a 3D film, you're actually doing 2 4K streams. This ends up being very, very high bandwidth, somewhere in the neighborhood of 10 to 12 gigabytes per second of bandwidth on an editor workstation. And worse yet, it's not only high bandwidth, it's also low latency, because we have human beings involved that are doing editing. And if you can imagine going back and forth, if you can imagine an old days with a jog dial, if folks know what that is, you're looking at video and you're going back and forth and looking at it, you want that latency to be as low as possible. So NVMe can do that, but the problem was they couldn't jam enough NVMe into the workstations because they ran out of PCIe lanes, because these workstations are using very high-end GPUs, sometimes multiple GPUs. What they could get was 1 or 2 network cards in there, and they can access this over the network. And then the way NVMesh integrates with file systems such as GPFS, such as BGFS, including legacy file systems like StoreNext, we can go ahead and access this flash at the exact same speed and bandwidth as if it's local to the workstation, yet it's a shared single namespace. So you can have multiple editors working on the same film or handing off things to each other without copying over the network. So very, very high utilization of NVMe, and eliminate copies was what Technicolor did there, while getting the performance of local flash. SciNet, now again, we jump to a totally different area, trying to show you, how flexible NVMe over fabrics and specifically NVMesh can be. SciNet is Canada's largest supercomputer. It's in Toronto, sponsored by the University of Toronto. And there we went in with our partner Lenovo, and out of only 80 devices, that is across 10 servers, so 10 2U servers, each with 8 NVMe drives, giving a total of 80 NVMe, we're getting 250 gigabytes per second of aggregate bandwidth. And this really shows the importance here of a scale out solution versus scaling up only in the chassis. So by us having a scale out solution, we actually stripe our volumes across multiple servers, and you can go ahead and have a single logical volume striped across as many as 128 target servers. In this case, we're using multiple sets of servers here, and obviously since we have 10 servers, they're not striped terribly wide. But by aggregating that pool, we're getting 250 gigabytes per second and up to 20 million random read 4K IOPS in only 10 servers. They're using this, of course, for a burst buffer, for local scratch, and then for certain compute jobs that do very, very high transactional 4K reads. So the beauty of NVMe is it can sustain high bandwidth, but also very high random IOPS. And of course, this is how the supercomputer there is doing that with our partner Lenovo. And then lastly, again, jumping to another use case. I actually really liked, Joel, I really liked your graph showing the adoption curve. I think that is perfect. And it really exemplifies what we also believe. Generally, we don't go after what we call the Super 8, some say Super 7. We go after that next band you had of the next 200 or so. And then we also go after what we call innovative enterprise. So I agree with your graph that enterprise will be slow to adopt. But within every enterprise, there is a part of it that we dub innovative enterprise, the ones that have to be at the cutting edge. And this is how we view our partner CMA. CMA does very high performance analytic databases using a very traditional enterprise tool, and that is Oracle. But they take Oracle to places it's never been before. Now with this, what they found using NVMesh was they cut their licensing costs by 62%. You may say, how is that possible? Well, Oracle's licensed per node. They're using Oracle RAC here to do analytics. And they had 8 Oracle RAC nodes going up against about $1 million array. I won't mention whose it is, but a very traditional array with all flash. And their I/O was still the bottleneck, especially latency, because in a very high transaction rate, latency becomes key. When they're doing full index scans of this database, bandwidth was key. So of course, we performed very, very well there. They replaced this entire setup with a total of 7 servers total, 3 Oracle RAC nodes and 4 NVMesh target nodes, with the volume striped across all the nodes. They did the same amount of work in this use case with only 3 nodes that they were using 8 nodes for before. Each node was getting a little over 22 gigabytes per second of bandwidth. Again, this is RDMA based, and with NVMesh, we seamlessly aggregate multiple RDMA NICs. So in this case, each server had 4 ports, but 2 cards. And we're aggregating the bandwidth of those cards seamlessly. So it works both for aggregation in an active-active sense, but also for failover. So if one of those cards or links goes away, we just keep using the surviving links. And this is all done without any configuration by the user. You don't have to set up anything like link aggregation protocol or touch the network ports. there. So RDMA really is not as hard as some people make it out to be. And in this case, they need the very low latency. They needed local flash latency, but they also need very high bandwidth for those full index scans. In a newer cluster that recently just got deployed, they're doing over 150 gigabytes per second of full table index scans in Oracle RAC. So we're very, very happy to have CMA as a partner, both as a customer and a reseller partner there. And I'm very happy if people want to ask questions about that later. And so just to give you an idea here of what I talked about, we're also talking about density. We are a software company. We don't sell any appliances. We only sell software. However, if you want the convenience of a single throat to choke, we offer that as well. I mentioned earlier, Boston was one of our first partners to offer the Talon. I believe that was offered over more than a year ago, about a year and a half ago. You could buy a Talon appliance from Boston. And very happy to recently have announced Lenovo. So Lenovo as full partner, you can buy a fully integrated solution from Lenovo if that's your choice there. And we'll be happy to announce others fairly soon. So you can buy an appliance if you want. What's pictured here happens to be, some people might recognize, it's a super micro node. That we also offer one of these through our partner WD. We offer a WD offering that's 4 nodes in only 2U, and we are the highest performance density in the industry. In the single 2U box, we have protection against a host failing, which we also believe is very, very important. You can't just have a host fail and have your volumes go away. So we stripe our volumes across nodes and across drives. So with this single 2U solution, you can get up to 80 gigabytes per second of bandwidth and nearly 20 million 4K IOPS, yet you can have any one node die, or you can have up to 2 drives die, any 2 drives. So HA solution, only 2U, extremely high performance, and this is representative of what you can order off the shelf or you can build yourself. And with that, I'll hand it back.
Thanks a lot. Those are some great use cases, Josh. I think it just shows kind of some of the value of what scalability and that ability to scale to high levels. You know, one of the advantages that scale out has over standard arrays. Cam, I'd like to turn it over to you. You should have control now, so go ahead and take it over.
Great, thank you very much. Hi everyone, my name is Cam Eshki. I'm with Lightbits Labs. For those of you not familiar with Lightbits, we are an Israeli-based startup. We have offices in Silicon Valley and New York City. And what we build is a software-defined disaggregation solution that separates storage and compute, allowing them to scale independently. So I'll talk about our perspective of the use case and where we fit in, and I think you'll see some similarities and some differences with some of the presentations you just heard. So, do I have control right now? There we go. So let me step back for a second and summarize from our perspective. You know, we are also targeting cloud service providers and enterprise private cloud. What are the requirements for this cloud infrastructure? On one hand, they want to be able to grow very rapidly to support more users, and with that, they need more performance, more capacity out of their infrastructure, and be able to support more services and applications on top of the same hardware. On the other hand, they also want to do this very efficiently. The idea is to be able to highly utilize the infrastructure you have to drive down your TCO, to have an architecture that's very easy to scale, uses standard servers, and, you know, again, software-defined model. So if you look at, Joel talked about this a little bit, you know, the architecture that for performance-sensitive workloads has been to use direct attached SSDs because you get a big fat pipe between your storage and your compute. And this is an architecture that's easy to deploy at small scale. The issue here is that you have a constrained ratio of compute to storage. Different applications have different requirements. As you scale, you end up with stranded capacity. You don't have enough capacity, storage capacity, you have too much capacity. And also data movement between the nodes could become an issue and create problems as you scale to thousands or tens of thousands of racks. So what we're seeing all the major hyperscalers do is move from this model on the left, which is using direct attached storage, to the disaggregated storage. And I'm talking about physically separating storage from compute. So now you can independently scale your storage and compute to create whatever ratio you need for a particular workload. you get much higher utilization of your infrastructure. You can independently upgrade and maintain your storage from your compute, which allows operational efficiencies. And now every compute node can get whatever size volume namespace that it wants and attach to it. And the key here is to be able to do this with performance that's equivalent to the left-hand side, performance that's equivalent to direct attached storage, and at the same time be able to use your existing infrastructure. So those are two important things. I mean, the concept of centralized storage is not new, but to be able to do that within your existing infrastructure and to get performance that's from an application point of view indistinguishable from direct attached storage is key. So what do? In a nutshell, we help our customers move from that direct attached SSD model, the converged model, to a disaggregated model where they can use a remote pool of NVMe SSDs with very low latency and do that without having to touch the clients and without having to change the network. Now, one of the things we did 3 years ago is we proposed a new spec for NVMe over TCP. Back in summer of 2017, we did a demo jointly with Facebook and got a lot of attention. We basically demonstrated that you can get very low latency with NVMe over TCP with our solution, and got the attention of the industry and the NVMe working group. And I'm happy to say that we were able to basically pioneer this and take it all the way to standardization, so that now it's one of the transport options for NVMe over Fabric as of last year. So with our solution, which is entirely on the target side, there's an optimized NVMe over TCP target layer. And we also have a software layer called Global FTL, Global Flash Translation Layer, that is managing the SSDs and getting the most out of those SSDs. So the combination of those two is what we call LightOS and is our software solution. So with this, you get much better utilization than what you would with direct attached storage. You're able to scale with simple, efficient TCP/IP across the entire data center, such that any compute node can talk to any storage server within a large data center. We also have an acceleration card, which is optional, and this is a PCIe add-in card called the Lightfield. And that card provides acceleration of certain data services when the storage server doesn't have enough CPU cores. So you can get those wire speed, you can get those data services at wire speed, and do implement features such as compression and erasure coding that you cannot do with the direct attached model. So how does this all fit in? If you look at a data center and you put all your clients in this diagram on the left-hand side, that's where you're running your applications, Cassandra, MongoDB, high performance analytics workload, whatever it is. All you need on the client side is NVMe over TCP drivers. And we've upstreamed NVMe over TCP client drivers. They're available in Linux, so you really don't have to do anything on the client side. There's no proprietary software running on the clients. There's no RDMA NIC requirement, just standard TCP/IP, and there's a standard data center network connecting everything together. Our solution is sitting entirely in the storage server. So the storage server is an off-the-shelf server. It just needs a bunch of NVMe SSDs. It could be Dell, HP, Supermicro, Quanta, whatever server you'd like to use. Runs our software. There's the optional acceleration card that you get all the features in software only, or you can use it with the acceleration card to boost the performance. And then all of the SSDs that are inside of the storage server, that entire capacity is virtualized and can be connected to compute nodes anywhere in the data center across multiple hops of networking. So there's two components to the product then. There's the LightOS, software-defined storage, which includes our target side NVMe over TCP and the management of the SSDs with our global FTL. And through that, you're getting an optimized NVMe over TCP stack on the target side, which does do flow control and reduce some of the potential packet drops you can get from NVMe over TCP/IP because of the TCP/IP transport. You also get data services such as thin provisioning, erasure coding. If an SSD fails, the data is protected, the service is uninterrupted. There's wire speed compression, There's quality of service features that allows for different namespaces to, essentially different applications to share the same pool of storage and get consistent latency and performance. And things that we do in the global FTL to reduce latency, for example, serializing all the writes and avoiding conflicts between reads and writes to avoid latency spikes you can get in individual SSDs. So with the global FTL, we were actually able to get better tail latencies than you would with direct attached storage. And we can reduce the write amplification, which will give you better endurance than you would with direct attached storage. The other piece of our solution is this card, the light field acceleration card, which is a storage acceleration card. And this works with our software. So it's not a standalone product, but it works with our software to provide data services at wire speed, such as compression and erasure coding. And some of the NVMe over TCP acceleration is done here, as well as global FTL acceleration. So the combination of the LightOS software and the light field is the LightBit solution. We offer it either as a software only or as a bundle of software and hardware. And if a customer wants a complete appliance, we have a partnership with Dell where the customer can buy the complete appliance either through Dell or from us with LightBit's branded product. So what are we seeing in the market? On the top is direct attached storage, high performance. As I said earlier, there are issues with underutilization of infrastructure when you're only using this converged model. And we are addressing that by delivering the same performance of direct attached, very close to direct attached performance, and in some cases, like with tail latencies, even better than direct attached, but in a model that's much easier to deploy and scale and get better utilization and drive down your cost. And you get the data services that I mentioned versus direct attached. Then you have traditional SAN infrastructure where you have centralized storage, you have data services, but the performance is low. And if you were to compare LightBit's NVMe over TCP solution to iSCSI, for example, you get significantly higher orders of magnitude, higher performance than what you can get with iSCSI, both in terms of latency and IOPS. And then you also have rack scale storage. We believe that RDMA fabrics are great for smaller deployments where you have one or few racks, where you can control the, set up the network properly for RDMA, and you can have RDMA NICs in every node, and you can deal with some of the challenges of RDMA. But once you go into a large data center where you have thousands or tens of thousands of racks, our customers are struggling to get RDMA to work at that scale. So it's very difficult to deploy RDMA at scale, and that's where the LightBit's NVMe over TCP solution addresses much larger scalability. Now, let me talk just briefly about performance. When you look at IOPS, and I'm going to start with the top right here, latency versus IOPS, we are able to keep the latency basically flat and at a very low level until you get to the maximum performance. Now, our performance is a function of the underlying hardware. Depends on how many SSDs you have, what sort of network connectivity you have, what sort of CPUs you have in the storage server. But in this example, this is a Dell 740XD, which has 8 SSDs and 100 gigabit Ethernet connectivity. And you get to 5 million IOPS, and you can see how the latency is basically flat until you reach the maximum IOPS. And even more interesting is if you just look at the canonical latency on the bottom, you can see that with NVMe over TCP, we're able to get very low latencies. And this is with wire speed compression and erasure coding. Write-only latencies that, when you look at the tail latencies, under 200 microseconds, and read-only at under 300 microseconds. So to wrap it up, what we provide is a way to disaggregate storage and be able to access a remote low latency pool of SSDs. The way we do this is with a software-defined model, so our customers can use their own hardware or any storage server that they like, which gives them a lot of flexibility and drives down their costs. We do provide a intelligent way to manage the SSDs with our global flash translation software layer that improves the endurance of the SSDs, reduces the latency, and provides these data services. We are using NVMe over TCP. We are able to use vanilla TCP IP network and deploy at scale with our optimized target NVMe over TCP, which relies on standard client drivers. And the last point is that we don't touch the clients. So when we go into a data center, we can just drop in the storage server running our software, connect to TCP, and you're good to go. You can connect any compute node to the storage server and carve out the available capacity any way you like. So it doesn't require any proprietary hardware or software on the client side. Thank you very much.
All right, guys, thank you. Let's go to our first questions here. Let's see, make sure that, yeah, thank you. We're running a little behind, so I'll try to make these a little quicker. So the first question we have is, what do you see as the leading use cases today for SOFS solutions? Try to keep your answer to a minute if you can, guys. We already covered a lot of this, but we'll start with Joel.
Sure. The primary use case is a primary storage for cloud native infrastructure for that not the Super 7, but the next 100 or 150 customers that are building private clouds at scale and need networked storage that is performant and inexpensive.
Perfect, thank you. Cam, I think you already answered this, but if you want to take another shot at it.
Sure, I'll give you an example of one of our customers who has us in an actual production environment where they want to put a storage server in every single rack and then be able to service not just the rack, but have east-west traffic to compute nodes anywhere in the data center. So you can create a cluster based on the workload that you want to run with whatever ratio of storage to compute you need for that application. And you're completely flexible with any-to-any connectivity. You run your workload, and then you can free up your resources and move to something else. Primarily, this would be for, we've seen a lot of operational workloads like SQL, NoSQL databases, time series databases, but also sometimes analytic workloads.
Perfect. And then, Josh, do you have anything to add besides what you talked about earlier?
Very briefly, I agree with both Cam and Joel on the infrastructure for web services. Our biggest customer to date is a large web scale property here in the Silicon Valley. They have thousands of licenses, so that web scale infrastructure of in the rack, very, very key, but also enabling east-west as well as north-south. But secondarily, I'd say we're seeing AI come up very, very fast in that when you do small test sets, you don't need a ton of bandwidth. But when you're looking at geospatial images, when you're looking at medical imaging with high resolution MRIs and things like this being at a terabyte per image, you need huge amounts of storage, so much so that you can't fit it into a GPU server. So we're seeing AI come up as another leading use case as well.
Yeah, I think that's a good point. I know more than a few people in the area that deal with medical and radiomics and things, and that is definitely one of the use cases that's important for NVMe storage in general, and I think for SOFS. All right, with that, I'll jump to the first audience survey. I'm going to go ahead and launch the polling. So the question is, does SOFS look like a solution that makes sense for your organization? Just check one of the answers. We'll give you a minute to do that. And while we do that, we'll go ahead and start the next panel question. And the second question is, and we'll start with Cam and then go to Josh and then to Joel. But the question is, should SOFS solutions support scale out, more nodes, scale up, more storage per node, or both to be effective? Go ahead, Cam.
Yeah, I think it's basically scale out. What we see in cloud infrastructure, the unit is a node, and then you keep adding nodes as you want to scale out. However, there are more enterprise-oriented applications where scale up is also interesting. Now, of course, the difference between scale up and scale out is that with scale up, you can get better economics, but then you're increasing the blast radius on failure. So you have to think about the trade-off between TCO and blast radius. But specifically in enterprise, what I meant is that, for example, we have a partnership with VMware where vSAN customers are interested in being able to scale their storage independent of compute and not have to add an HCI node with software licenses and in order to just scale their storage, because storage is growing faster than compute. So they want to be able to drop in storage server that provides that scalability of storage. And then as they need more storage, they can scale up that node. So really, I guess the answer is both, depending on the type of customer.
No, it makes perfect sense. Josh, you want to throw in anything on this question?
Sure. I agree with what Cam said, and that both are very, very important. So you can't just scale in a chassis. That will limit your blast radius, but it also limits then what you can do if you run out of bandwidth or you run out of capacity. And I think for us, one of the whole points of a software-defined storage solution is to avoid that forklift upgrade. Even if you're buying an off-the-shelf Dell server, for example, once you exceed those 24 drives, if you want to make your volumes any larger, you want to be able to expand outside that chassis. And this is something that NVMesh has done from day one when we launched publicly way back in 2017. So we believe you should be able to scale up in a chassis, but scale out across chassis, including chassis failover. So we wholeheartedly believe that scale out and scale up are very important together.
Excellent. And Joel, what do you guys see?
Well, I'll be the counter case. I think this is a scale out only play, and that the days of classical scale up are limited. The reason basically is ultimately we will all want to be able to flow work around our infrastructure as demand changes and in order to get efficiency. And that can really only be done in a scale-out world. So I think this is a step on the way to a cloud-like infrastructure management. And you know, all of these customers on that sort of ski slope picture that I showed are at some point on that journey. And for some, it'll take a long time to get there. Others are already there. But this is an enabler for the journey to the cloud.
Perfect. And with that, let me launch audience survey question number 2. And by the way, we'll put all the results of these surveys into the slide set that will be available to everybody, as well as the recording of the webinar afterwards. But if you can go ahead and answer each of these 5 questions, it's just which of these capabilities are important versus non-important. We'll give you a couple minutes to do that. The poll should be launched. And with that, let's go to question number 3, which is when designing scale-out storage solutions, it's key to avoid bottlenecks anywhere in the architecture. I think Joel's slide showing the old architecture and networks was certainly illustrative of that as far as bottleneck capability. What steps should be taken to address congestion on Ethernet networks that now have to contend with all the strain and traffic of both storage and network traffic? And Josh, we'll start with you for that one.
All right, thanks, Mike. When we founded the company, we were and still are very, very heavy believers in RDMA and have added TCP later on, as there are times that we acknowledge that you don't need only the 5 microseconds of overhead that we can do with RDMA. Sometimes 180 microseconds, or depending on if you're doing a read or write or erasure coding, et cetera. Sometimes less than that is fine. But Cam made some points, and then Joel made some points when he talked about TCP as well being allowing oversubscription, and that actually drove the adoption of CLOS networks by the big guys. So now if you take that as a given, that CLOS has become the standard, that you have enough bandwidth, then that can be your storage network. And by enabling, for example, in RDMA, flow control, that was originally developed to do fiber channel over Ethernet. Now that may have a bad taste for some people, but it does make Ethernet function like a lossless fabric. Once you enable that, and it's not difficult to do for our customers at all, you get the best of both worlds. You get an extremely low latency, high availability fabric. And so we are believers there that you should go ahead when you want the highest performance, lowest latency, deploy RDMA. However, if TCP is good for you, then we can support that as well. So RDMA is a first choice for high performance. TCP would be secondary.
Excellent. Joel, what do you think on this?
Well, I think my perspective is a little bit different. I guess step one is don't panic. I mean, you need to do the math here. Very, very few application instances can issue 100,000 IOPS. I mean, there are a couple I'm aware of, but you know, 100,000 4K IOPS is less than half of a single 10 gigabit per second link. And so for the vast majority of cases, if you have 10 gig from your client nodes, you have more than enough bandwidth to run network storage. So in the near term, run what you got. Run TCP initiators at 1 by 10 or 2 by 10 gigabits per second, and you'll be a very happy camper in all but kind of the corner cases. The storage nodes obviously need to be connected to uplink ports at 100 gig, but that's a relatively small cost. And in the medium term, as your data center refreshes, you know, kind of ride the wave that the hyperscalers have driven for us. They've driven networking costs, and by that I mean the cost per switch port, the cost of optics, and so on, very hard. And so architect as they have for lots of bandwidth and low utilization. I mean, most of latency is queuing delay, not network transit. And so what you want is spend the money for lots of bandwidth and plan on low network utilization, because it will more than pay back in terms of flexibility and efficiency. RDMA, you know, use RDMA when in one of two cases. Either your environment's a walled garden and, you know, like dedicated storage backends or something where you control everything and you can you know, prevent network storms and so on. Or when Rocky matures, and to me, it's not ready for prime time yet, but extensions need to evolve to allow RDMA native loss recovery and hardened congestion control that works even when you have a babbling, you know, participant or something, and every NIC has RDMA offload. That's, I don't know, 5 years away or something. Then we'll all switch eventually, but in the meantime, TCP is going to get better pretty rapidly. It's good already, and it's going to get closer and closer to RDMA at a pretty good clip. So I think 99% of the world, you know, Lightbit's got it right. TCP was the way to go, and RDMA is a corner case to me, and it's very useful for some important corner cases, but it won't be ready for adoption in the kind of wild west of your cloud infrastructure for a while.
Excellent. And Cam, obviously as a company that is focused on TCP networks, I'm sure you have some opinions on this one too.
Yeah, I think I agree with what Joel said and some of the points that Josh made. I think basically with NVMe over TCP, you get a very simple and efficient way to connect everything up together. It does not require lossless network. It doesn't have any interoperability issues between different vendors the way RDMA does have. And what we're seeing from customers is, what do they really want? They want consistent low latency. And the consistency is also important. And this, by the way, is much more important than the IOPS, at least in the applications that we're seeing. So one of the other major contributors to latency is the SSD itself. So, we've done things not just to improve the latency you get out of the network, but also to improve or reduce the latency of and tail latency of the SSDs, which does contribute significantly to what latency the application sees. So overall, to answer this specific question, what we're seeing is that our customers are building out their networks such that the network is underutilized today. There's plenty of headroom to be able to support storage over the network. And if it's done right, then you can very easily fit in to the existing network and not have to make any changes, not have to put any special NICs on all the clients, and very, very easy to deploy at scale, which is a good trade-off versus the extra, let's say 20 microseconds or so improvement in latency you can get out of RDMA. I think there, as Joel said, there are use cases that can benefit from that extra optimization of latency, and as long as it's a smaller deployment, it can be managed and deployed with RDMA. But most of the customers that we're talking to, pretty much all of them, when they're talking about sort of an any-to-any connection within the data center, they have not been able to get RDMA to work at that scale. Yet, at least.
Very good. Let's go to the last audience survey question. And while we do that, then we'll jump into the last panel question. And this question is, how do you see SOFS fitting into the overall storage solutions environment? So if you had to say, is it important? Is it a game changer? Is it useful, interesting, or we don't see it as relevant? So I'll go ahead and launch that poll. You should see it show up on your screens, and you can go ahead and answer questions for that. And with that, let's go to the last panel question, and that is, what new application deployment opportunities do FOS solutions open up for users? And we've talked about things like AI. Are there any other things like that you guys see that are kind of new things, not just doing the old things that we do today, but new things that we can do? And we'll start with Cam at Lightbits. Cam, go ahead and take it.
Sure. Yeah, I think AI is a very interesting one. If you look at how AI is deployed today, you have a more traditional enterprise storage box that takes in the entire data set that, let's say, machine learning servers are using for training. And then each machine learning server has direct attached SSDs inside that functions as a cache. So they take a subset of the data from that enterprise storage box, they put it in the machine learning server's SSDs, and then that feeds the GPUs. Well, that model, the problem is that the storage box isn't fast enough to be able to feed the GPUs on its own. The SSDs inside of the machine learning server could be too little or too much. Most of the time, you may not use all of it, so you're wasting that resource. Well, that can really collapse and converge into a single box with NVMe Fabrics connectivity that can feed the GPUs and can fit the entire data set. And so now in the rack, you have this server that has a bunch of NVMe SSDs and connects to 3-4 machine learning servers, and you no longer need that cache layer inside of the individual machine learning servers. So you're converging that direct attached SSD with the more traditional enterprise storage, which gave you the capacity and data services. So this is a very interesting use case. I think in general, the point is that with SOFS, what you're getting is composable storage where you can actually deliver NVMe as a service inside of a data center or in edge applications where you don't have to worry about managing direct attached SSDs, but you still get that type of performance with whatever size volume that you want. It could be 1 terabyte, 10 terabytes, 100 terabytes. You attach it to your compute node, and not only do you get operational efficiencies, but you get this composable storage flexibility.
Excellent. And Josh, you guys see any new applications? You talked about AI. Are there any other ones that you've seen in some of your deployment scenarios with your customers?
There are new ones. I want to comment on something Cam had said. I fully agree with Cam that these solutions really open up AI, but where I very much disagree is that if you look at these solutions from NVIDIA, for example, with DGX1s, DGX2s, and almost anybody else doing a GPU server, the thing that's included in all of these is Mellanox networking, either Rocky Ethernet or InfiniBand, and these are RDMA. There's a reason these two go together is because the GPU to GPU server communication is all RDMA based. So I hesitate to see where, if I was deploying a farm of GPU servers, why I would use RDMA for the lowest latency communication between the servers and then switch to TCP for the storage when I already have RDMA deployed. Now, you can also use this going to the new use case in Edge. Cam also did mention Edge, but what's most important in Edge now is you have very, very limited power and cooling at the edge. And so deploying NVMe drives, which the high performance ones can still burst to over 25 watts each for writes. If you're not getting maximum efficiency out of those, you're drawing more power at different times. You're spending a lot of extra money. So when you have this very tight constraint and you need high performance, you need high performance density. So we're seeing folks think about things at the edge using shared NVMe rather than using direct attached. And this is especially in the AI world where you're doing inference at the edge, you're doing training in regular data centers. So we think that we're opening up new use cases with SOFS at the edge, especially for inference in AI.
Well, and certainly with NVIDIA acquiring Mellanox, or the pending acquisition, I don't think RDMA will be going away in the AI world. So I think that's an interesting point as well. Joel, what do you think? Are there new application deployment opportunities you guys see from SOFS?
Yes, it's a necessary but not sufficient condition for one of the biggest revolutions in IT management, and that is simply dynamic workload blending and elastic scaling. If you look at any public-facing SaaS or web services company, they all suffer from demand spikes. You know, if you're a marketplace, you know, Black Friday, your traffic is 3x the background rate or whatever. And today, the way you handle that is you buy 3x the number of machines, and they sit idle, you know, 364 days per year. But yet, those companies all have a big AI team that's trying to grind along optimizing models for, you know, what ad to show the customer or whatever. And those guys never have enough machines. And so you have this bizarre situation of a data center full of machines that sits idle most of the year, and another group of people that just couldn't get enough compute hardware if you gave it to them. And what they lack is the technology to move capacity between the two dynamically and to respond dynamically to spikes. That sort of elastic workload blending requires the ability to run any instance on any node. And Google has proven and published that, you know, any sort of locality constraint is tying the hands of the orchestrator and will cost you money. And so if you want to run any instance on any node, it needs to be able to see its storage from any node, and that means network storage. So this is a key brick in the path to optimum workload management, and that saves you. You know, we all make flash utilization more efficient, but that's kind of the table stakes. Saving, you know, 30 or 40% of the compute node count for the same work is kind of where the real pot of gold is, and that's what we enable.
Very, very good point on the application side too. I mean, I think as storage people, it's very easy for us to think that storage is kind of the center of the universe, and
Right.
Obviously data is incredibly important, but at the same time, if you can't run your applications because all the bandwidth is eaten up, that's a problem. Well, so with that, let's jump into the Q&A. We have two questions. I'm going to take a shot at our second question first and let you guys jump in. The question is Ethernet fabric or switch is faster or low latency than SAN or InfiniBand? Certainly from a bandwidth standpoint, Ethernet is as fast as InfiniBand or very close. It's faster than SAN. I used to be a fiber channel guy, so I don't say that lightly, but if you look at 100 gigabit Ethernet, it's certainly faster than 64 gigabit fiber channel. When it comes to latency, obviously that depends on a variety of things. So why don't we go ahead and start with you guys. I don't know if Josh, you want to take it first and give your opinion on this one?
I think you hit it basically on the head, Mike, which is your mileage may vary. In our testing, we test very, very regularly between Ethernet and InfiniBand, sometimes even on the same hosts. In that Mellanox has a card, the VPI cards can be either InfiniBand or Ethernet. And we see extremely little difference, maybe in the 1 microsecond area at the link layer. So link layer is the same, but in overall processing, it's maybe 1 microsecond different. Your points, though, against SAN are extremely valid. Look, the strict answer to the question is SAN fiber channel is going to be the slowest. It's behind in bandwidth. 128, is being pushed now, but then we're going to get 200 and 400 gigabit Ethernet, so it's behind in bandwidth. As far as latency, it depends on which fiber channel you have. The very latest fiber channel, again, if you could afford 128, it's getting down there in the link layer for latency, but it's still based on SCSI. So, the protocol you add on top is going to make a big difference.
Absolutely. Cam, what do you think?
Yeah, I agree with what Josh was saying. I think, well, InfiniBand is low latency. It's not an option for many of the cloud service providers and some of the customers that we're targeting. They don't have InfiniBand networks available. I think in enterprise, we do see fiber channel and NVMe over fiber channel. It's more of a brownfield deployment where they already have fiber channel and they want to extend the use of that as much as they can. So with anything new, we're seeing Ethernet really dominate, and it's just a much simpler way to deploy at scale.
Joel, what do you think on that question?
Well, if you want to understand why it won't be possible for fiber channel or other technologies to keep up with Ethernet, just Google Tomahawk 3. This is a single chip Ethernet switch with 12 terabits per second of cross-sectional bandwidth. Somebody else paid for the development of that. You can just buy it. And if you're in the InfiniBand or fiber channel or any other transport, it's not the link layer cost, transport cost. It's the switch that's a big lift to develop. And the hyperscale guys are funding, essentially subsidizing the development of these enormously high cross-sectional bandwidth switch chips. And that's just going to make, large capacity Ethernet networks are just going to be much cheaper to build, not because of anything that's particularly great about Ethernet, but because there's, somebody else is pouring enormous amounts of money into funding the infrastructure. So that's really the big nugget here, is that there is an economic incentive for very, very high bandwidth networks. And that economic incentive, by the way, is the workload blending one that I just mentioned previously. That requires network locality and low latency, and as a result, the big seven have funded that, but they funded it with Ethernet as the transport.
Yeah, and that's a really good point. I mean, again, having a lot of history in fiber channel, none of the big sevens are using fiber channel in their data centers. For the mainline business source side, they use it for business applications on billing and things like that, but
right.
Certainly not in the big massive data centers that people think of. I think it's really a bigger question. The question always used to be, do you want to have a dedicated standard on? And that was true whether it's fiber channel or InfiniBand in the case of HPC. I think with a lot of the new speeds coming out with Ethernet and a lot of the virtual networking capabilities, that question has become less important than it used to be, say, 10 or 20 years ago, or even 5 years ago. So with that, let's jump to our next question, which is and I'm not sure who this was targeted to, but the question is, what kind of compression is done and how do you do it at wire speed? So, Cam, do you want to take that one first? We'll go through each of you and you can talk about what you're doing there.
Sure. So we do, the details can be provided under NDA, so visit lightbitslabs.com if you want to learn more and engage with us. But we do compression at wire speed. If you use the acceleration card, then you're essentially offloading the server CPU, the storage server CPUs, and are able to provide that at wire speed. So the performance numbers that I showed earlier, for example, were with compression running at wire speed. So it's the combination of the hardware acceleration card with our software that's able to achieve that level of performance. I don't know if that answers the question.
Yeah, absolutely. Joel, okay. What are you guys doing as far as data compression goes? And I suppose as well.
You're breaking up a little bit there, Mike, but we do not offer compression today, and I'm of course precluded from talking about things that are in the roadmap, but are a little further out. The all of us, I think, are able to produce a level of performance that makes the network the bottleneck for any practical network interfaces. And so if the compression's on the target side of the network, you haven't helped that. You've helped storage density, of course, but you haven't made the overall solution more performant. And so we're looking at various implementations of compression and other, other data reduction techniques, but don't have anything to say about compression algorithms today, except that if you're willing to work hard enough, you can get probably a little better than 50% compression on anything that's compressible, and if the data is encrypted by the initiator, which is more and more common, then it's not compressible. So that's kind of a limit to the overall efficacy of compression, is the fact that increasingly, if you want security, the only way to assure yourself that there are no breaks in in your data security path, or to encrypt the application and send it to the storage subsystem encrypted, and then decrypt it when you get it back. And if you do that, compression's off the table. So there are pros and cons, of course. Right now, we haven't chosen to emphasize compression yet.
Josh, that's great. Thank you, Joel. Josh, what are you guys doing on this area?
We're very similar to what Joel was saying, is that we had explored doing compression, and we actually had customers say don't in the use cases that they were doing that. If you look at M&E, such as the Technicolor use case, we're already dealing with generally compressed video, so that's not going to compress. A lot of the databases are already optimized and doing compression, so we haven't offered that. Now, that said, what we have publicly announced is support for SmartNICs, such as the one Stingray from Broadcom and Bluefield from Mellanox, and those chips do offload things like compression. So if that comes out soon, without again disclosing anything NDA, we would probably use those to go ahead and offload those tasks.
Very good. And I think it certainly illustrates the challenge that we've always had of security versus compression versus, do you do this on applications? Do you do it, in the storage device? It's a never-ending battle, but yeah, I agree with everything everybody said. Well, thank you, everybody. That kind of wraps up our webinar. As a reminder, we'll be sending out a link to the recording of this webinar and a link to the slide set in approximately 2 days. Thanks again for joining us, and we look forward to doing more webinars with you and having you join us on others. And thanks again to our panelists from Toshiba, Lightbit Labs, and Accelero, Josh, Cam, and Joel. Really appreciate you guys sharing your thoughts with our audience. Thanks again.
Thank you, Mike. This was great.
Bye-bye all.